All right. Hello, everybody. Welcome to VSA Online. Today, I have a pleasure to greet Marta Lewis from UK, from University of Bristol. But I know that she is on sabbatical, so she will tell more about her current temporal affiliation. So, without any further delay, so I look forward to your exciting talk, Marta. So, please.
Okay, thank you very much. Thank you very much for inviting me. I haven't talked to very many people in this community before, so it's really nice to be here and to kind of talk to you all. So sorry, I don't know how to pronounce your name properly.
It's Evgeny.
Evgeny, yeah,
Yes.
sorry about that.
No worries.
Yeah, Evgeny. So, as Evgeny said, I'm currently at University of Bristol, but I'm currently on sabbatical and I'm working at the Santa Fe Institute. My current kind of area of research is in analogy making, which this talk doesn't really have anything to do with, but I'd be very open to chatting with people about kind of analogy formation and analogy representation within VSAs. So I'll get on with the talk. So I'm going to talk about a recent paper of mine, which is it's very much sort of work in progress. It's very much kind of initial steps towards certain things, which I'll hopefully explain to you. So do stop me at any point if you have questions about what I'm saying. And also a caveat that if I have not cited certain people properly, I apologize. Please tell me, speak up or put it in the chat, so that I can make sure that I kind of really get to know the kind of work in the field, because as I say, I'm kind of new to this. Okay, so I'm going to talk about compositional vector semantics in spiking neural networks. And I noticed that the talk 2 weeks ago was about the very spiking neural networks that I talk about in this talk. So if you were at that meeting, you probably know at least as much, if not more, about it than I do. So yeah, if you have points to make there as well, that should be good. But anyway, there's a nice kind of continuity, a nice little intro for you. And there's an archive paper for this, which actually it's published under the name Compositional Vector Semantics, but actually on archive for some reason it's called Grounded Learning for in spiking neural networks or something. I can't remember. So anyway, I've put that archive link in the chat if you want to kind of read along with the presentation. Okay. So what am I going to talk about? Basically, I'm going to talk about a kind of something that isn't vector symbolic architecture. I'm going to talk about something called compositional distributional semantics, which has some really strong links with vector symbolic architectures. So compositional distributional semantics, at least the kind of branch that I'm going to look at, is a way of uniting symbolic and distributional approaches to language. So meaning basically, we've got good ways of representing language symbolically via grammars and so on. And we've also got good ways of representing meanings of words as vectors. And compositional distributional semantics is a way of unifying these two approaches. And I'll give an overview of what it is exactly. I'm going to argue that compositional distributional semantics may have some benefits over certain VSA approaches to language, but I would have to discuss this. If I say something that you disagree with, I would really love to hear, I would really love to talk about that and find out more about how people, approach language with VSAs. Compositional distributional semantics is purely text-based and it's not cognitively motivated at all. And I think that this is a drawback. There's no kind of inbuilt way of mapping from kind of other representations like images or sounds, or you can imagine an agent that is getting signals from the environment. There's no way of kind of taking those and dealing with them within this compositional distributional framework. It's much more, it's just a purely text-based approach. And as I say, it's not cognitively motivated. It's really just a way of thinking about how to build meanings of words from large corpuses of text. So what I'm going to do is present a mapping from these compositional distributional models to holographic reduced representations, and thereby give a mapping to the spiking neural architecture NENGO. What I'll do is I'll give a kind of overview of the mapping, and then I'll present a very small toy implementation that I've done. Okay. So integrating neural and symbolic approaches to language, or distributed and symbolic approaches to languages, which I guess is something that you are all vaguely interested in, like I am. So how does the categorical compositional distributional approach work? So the idea is that on the one hand, as I say, we've got a good way of describing how words combine to make meanings of phrases or meanings of sentences and so on. So we might have like, we could have a vector, we could have a representation of red, and we have a representation of car, and we know we want to kind of put those two things together in a way that the thing that comes out is a red car. And grammatically, we can describe how we do this. So we're going to use a particular kind of grammar, which has types, and we're going to use a very simple form of that grammar. So lots of people work in this area and use much more fine-grained types than this, but here we're just going to use two types, N for noun and S for sentence. So we think about these types, N for noun, S for sentence, and then each type has left and right inverses. And you can also concatenate types together. And so what we get here is, for example, this concatenated type of an N concatenated with an NL is the type of an adjective. So here, in English, if you have an adjective to the left of a noun, then you can kind of cancel out you can combine, the adjective and the noun to get an adjective noun phrase. And then this type here, this concatenated type here of NRSNL is the type of a transitive verb in English. And so in English, if you have a transitive verb and you put a noun on one side and a noun on the other side, then you can cancel out, you can kind of think of these types as cancelling out here to give you a sentence. And so we form a string of types, and if that string of types reduces to the sentence type, then we judge it to be a grammatical declarative sentence. Okay, so this is purely symbolic, and it's very similar to like a standard grammatical tree that you might have seen before. Now, in the categorical compositional distributional approach, this paper by Baroni and Zamparelli had the title Nouns are Vectors, Adjectives are Matrices. So we basically take this grammar and we build representations that we can plug into the symbolic structure such that the type reductions on the grammatical side correspond to some kind of operation within the on the semantic side. And in this case, we're going to plug vectors into this into noun types. We're going to plug multilinear maps into things like adjectives and verbs, and then these grammatical type reductions then correspond to tensor contraction. So if you are unfamiliar with the term tensor contraction, you can think of it as basically just multiplying. It's like a kind of beefed up version of matrix multiplication, sort of operating over multiple kind of dimensions of a representation. Okay. And so this is this is the model that I work with, and I do, you know, I've done lots of I've done a whole range of research here. One of the kind of areas that I look at is what sort of other things can you plug in at the top here instead of vectors and linear maps, and what sort of things can you do in terms of reasoning and so on and so forth. But as I said, these representations are usually learnt from text, just big corpora of text. They usually don't have any relation to other forms of representation like images and so on. And they're not at all cognitively motivated. There's no kind of thought of being cognitively realistic here. So yeah, so that's this approach. Do people have questions here that they might, any kind of clarification questions at all?
No, let's ask. So, do we have any questions? Immediate questions?
It's fine if not.
Yeah. Okay. Good.
Yeah. Okay. Cool. And then we have, on the other hand, so you know, thinking about the kind of title slide was integrating, you know, distributed and symbolic representations. We have other forms of doing that. So one thing might be using role filler bindings introduced by, well, this particular form introduced by Smolensky, where we again have a kind of symbolic structure here, which maps to a distributed structure here. And there are lots and lots of different variants of this. But benefits of this are, obviously, we have a kind of compositional aspect. There's also this systematicity aspect, which is potentially lacking a little in the previous model that I talked about. And also the nice thing here is that these are used in more biologically realistic neural architectures. So I'm just going to talk about the semantic pointer architecture, which is used by Elias Smith in this kind of spiking neural network architecture that we that I'm going to look at. So what Elias Smith does is he uses plates kind of VSA of holographic reduced representations, and I'm guessing most of you are probably very familiar with this, but I'll just go over it anyway. So we've got this notion of kind of, you could call it superposition, you could call it just kind of collecting things together, where you can have a vector that's basically formed out of the addition of two other vectors. So you're just here, so this addition you can think of as, well, I think of it, and I'd love to discuss, think of it as kind of collecting representations together. We can also have the notion of binding. So we might have two representations that we want to bind together. And so thinking about something like adjective noun combination, if we've got, let's say, an image of a red cube and a blue sphere, when we represent that image, we want the redness to be bound to the cube object and blue to be bound to the sphere object, rather than just kind of collection of something red, something cubical, something spherical, something blue. We need for adjective noun combination, we need those things to be added together. And to do that, Plate uses a circular convolution, which looks like this. And then there's also an unbinding mechanism. So the unbinding mechanism is called circular correlation and looks like this. But it can be approximated by permuting the entries of vector slightly and performing circular convolution. I'm actually not going to go into that in too much detail. But yeah, so we have this idea of kind of collecting representations together via superposition. We have a notion of binding representations together, and we have a notion of unbinding a representation from another. Okay. And as I said, Elias Smith presumably with a whole team of people, has implemented this in this software called Nengo. And so here's a picture which is just taken from their documentation. And what's happening here? So here we've got some representations. So the idea is that there's a spiking neural network architecture, and a vector can be approximated as a kind of pattern of firing of a collection of spiking neurons. And so here we've got, for example, we've bound together the neuron, we've bound together representations of red and circle. We've also bound together representations of blue and square, and then just added, though, you can just add them together to form a kind of collection. And then when you then prompt the network with a particular cue, so here we've prompted it with circle. The network can then output whatever the color of the circle is. So we can think of this as like asking a question: what property does a circle have? And it outputs it's red. Here we might think, so here it's kind of what is red, and it outputs a circle, and so on. So and this is nice. It's kind of nice and dynamic, and they argue that it is more biologically realistic. So I've talked a bit about this sort of adjective noun composition. And so I'm talking about, talking previously about red circles and blue squares and so on. But one problem that I have with a kind of naive approach to adjective noun composition is that it doesn't map the corresponding representations to the right thing. Okay, and so here's my example. So let's say we're going to do adjective noun composition just by binding things together. And here, so here I've used tensor product rather than circular convolution, but I think it probably holds. I'm not sure actually. We can revisit that. You can tell me if I'm wrong here. Okay, so let's think about doing adjective noun composition in a a fairly naive way, and let's just say, okay, well, to do adjective noun composition, we're going to bind the adjective, in this case fluffy, to the noun, in this case dog, and then let's say we bind fluffy to cat, and then we want to say let's compute the similarity between these representations. Let's compute the similarity between fluffy dog and between fluffy cat. And the way we're going to do that is just by taking the dot product of the two resulting vectors and see how similar they are. So when we do that, we get fluffy dot fluffy, which is just 1 because they're identical, and we get the dog dot product of dog with cat. So we've just got just a 1 times the dot product of dog and cat, but that is itself the similarity of dog and cat. And so my argument here is that actually we don't, this is not a property that we want. We don't want fluffy dogs. We want fluffy dogs and fluffy cats to be more similar to each other than just generic dogs and cats are. Okay. And this was kind of measured and investigated by Martin and Dumas, who looked at this in looking at human similarity judgments. I think Hummel as well. So what could we do instead? Well, we could do something else. We could do something a little less naive, and we could say, okay, well, we're going to say that I'm going to take a fluffy. I'm going to take the word fluffy and bind it to the representation of an adjective. Sorry, a role of an adjective here. And then I'm going to add that together with cat bound to the role noun. And then similarly with fluffy dog. And then we get some numbers which are a bit closer to what we want. So let's assume off the bat that cat and dog have similarity. If we just assume that cat and dog have similarity 0.5, then when we take the dot product of fluffy dog and fluffy cat, we then end up with 0.75. So now adding this fluffy adjective in has actually increased the similarity of the fluffy dog and the fluffy cat. So that's good. So why don't we just do that? So I would argue here that that sometimes we don't necessarily want adjectives to always increase the similarity. So you might have something like you might have the word bright applied to light and to student, and we might not necessarily want bright light and bright student to be any more similar to each other than light and student are, because they're really two different categories of things. What there's other examples might be if we have like open the door. Do we want a sentence like open door and open jar to be more phrases like open door and open jar to be more similar to each other than door and jar? Potentially a bit, but this notion of kind of just tying a kind of filler, an adjective filler to an adjective role and adding the similarity in maybe doesn't give us as much flexibility as we want. On the other hand, this compositional distributional approach, where we think of an adjective as a matrix that actually transforms the noun, does give us the capacity to make fluffy dogs and fluffy cats more similar to each other than dogs and cats are, but maybe doesn't do the same thing for, you know, bright light and bright student. Okay, so this is the sort of motivation, one of the motivations behind what I'm doing. Okay. So how can we go about mapping compositional distributional approaches to VSAs? So I'm just going to revisit the compositional distributional approach. I said we have nouns as vectors, adjectives as matrices. I would argue that we can actually we can kind of think of these things as having a relation to VSAs by again thinking about this binding and unbinding operations. So we have superposition, which is exactly the same. The binding operation we're going to take to be tensor product. So and I'm going to introduce some notation here. So I'm going to say we can then think of a tensor product of V and W as being a sum over these two indices of basis vectors EI tensored with EJ and multiplied by the relevant coefficients from the vectors V and W. And then unbinding is just going to be taking the dot product. So it's very similar to the tensor product representation of Smolensky. So if we've got a representation V, which is actually a binding, well, which is some kind of binding of or sum over bindings of vectors, then we can unbind another vector from it just by taking the dot product there. Okay. Any questions or comments so far? Okay, I'll just carry on. Feel free to just put questions in the chat as well. Okay, so we have this idea of we want adjectives to be nouns to be vectors and adjectives to be matrices. So we just choose a set of basis vectors EI for the semantic space, and then we can think of the car as just being a sum over these basis vectors with coefficients, and then a adjective red as just being a sum over the tensor product of the basis vectors, again multiplied by the relevant coefficients. And then forming this composite red car, we're going to think of it as essentially we're going to think of adjective noun composition as basically unbinding a noun from an adjective. Okay, and this makes it very easy actually then to map over to a kind of holographic reduced representation or semantic pointer architecture. So in Nengo, these semantic pointers, as I said, are basically just patterns of activation of kind of clusters of neurons, and so what we do is we choose a set of kind of basis semantic pointers for the semantic space. We form nouns. Nouns are basically the same thing. They're just superpositions of these kind of basis pointers. And then an adjective is going to be superposition of convolutions of basis pointers. Okay, so you can see, I mean, I've kind of written it deliberately, sort of similarly, so that you can see exactly how it maps over. And then again, adjective noun composition is basically then just unbinding the noun from the adjective. And what we'll get is we should get basically a kind of superposition of these semantic pointers that should represent a red car. It will, of course, be a lot noisier than if we were doing it in just kind of the space of vectors with tensor products, because using these using circular convolution means that there is going to be a lot more noise there. Okay. So now I also kind of take another perspective on this, which is the following. So we again just think of nouns as basically superpositions of like role vectors or role pointers. Superpositions of role vectors, let's say. And then adjectives we can think of as collections of filler role bindings, where the roles are the nouns. It kind of doesn't really matter how you conceptualize it, but let's say the roles are the nouns and the fillers are the adjective noun combination. So here, if we had red car, we would have sort of red, this would be car, this would be a vector for car, and this would be a vector for red car. Okay, and a collection of all of these with red in front should then form the adjective red. Similarly, for transitive verbs, if we have a representation of a sentence, a kind of holistic representation of a sentence, like you know, John kicks the ball. If we collect together these holistic sentences together with the arguments of the verb, tensor them together, and then add them all up. And again, we can then, so this is within a kind of tensor product, the vectors and tensor products, but we can again map these vectors to semantic pointers, and we map the tensor product to circular convolution. Okay. So here's just a really sort of toy example of what that would look like. So recall that I said an adjective is going to be a sum of kind of these holistic representations combined with the noun that corresponds to it. So we've got red is going to be red car. So we suppose here that we've got vector representations of red car, red apple, red wine. And we've also got vector representations of car, apple, and wine. Then red we think of as the sum of red car tensored with car, plus red apple tensored with apple, plus red wine tensored with wine. And then when you do the adjective noun combination, this unbinding, we will get back red car plus some noise. So I guess, you know, so you might be thinking like, well, what's the point of doing this if we already have all these representations of, you know, red car, red, you know, all these holistic representations already? Why do we even need to like form this adjective red? So the idea would be essentially that we then that given this that there might then be nouns that we haven't got this holistic representation for. So if we I'll give a kind of hand-wavy description of a training regime later that I want to kind of improve on. But essentially the idea would be that maybe an agent using these representations has seen, someone said to them, look, there's a red car, there's a red truck. And then someone says, you know, there's a lorry, for example. Then they can, the idea is that then you could form the representation red lorry, even though you haven't seen it, by representing red in this way and making the composite. Okay. Then of course, so the previous one was in the kind of field of tensor products and dot products, and then mapping tensor product to circular convolution, and dot product to circular correlation. We then get, you can then do the same kind of operation. Obviously, it's going to be a bit more noisy if you do this because because of the nature of the representations. And so here's the kind of learning strategy that that I would like to think about implementing. So we're going to assume that we've got representations of some nouns and adjectives, and we've got some labeled data. So if we haven't got representations of the nouns and adjectives, it doesn't matter, because we can just you can always just initialize your nouns and initialize your adjectives just using whatever you're given at the beginning. But let's assume that this agent has been learning for a little while and it has some representations. And this is a supervised learning strategy. So let's say, you know, the agent is told that this thing is a red car, okay? And so we're also going to assume, so yeah, a lot of assumptions. We're also going to assume that the agent has some means of going from a stimulus to a vector representation of that stimulus. So you know, if you're using this Nengo architecture, if the network is given a kind of stimulus that might be an image, it might be something, and that gets mapped to some sort of semantic pointer, which we're going to call RC for red car. And it's also told this is a red car. Well, then it can update the representation red by simply saying, okay, well, I know it's a car, so I'm just going to take my holistic representation RC, bind it together with car, and add a small multiple of that into my adjective. Similarly, to update car, we would go, okay, well, I've got I know it's red. And so what I'm going to do is I'm going to unbind the red car filler from red to give me whatever red car is bound to in red, or an approximation of that. Maybe it's only seen red lorries so far. And I'm gonna take that vector and add that into my representation of car. So yeah, I haven't played around with it. I've played around with this very vaguely, but not. I haven't got a really good working version of this. So this is something that I'd like to move on to. I think as well that these representations in the brackets are actually the derivatives of the kind of the similarity of the holistic representation RC with red unbound from car. So there's a nice kind of theoretical motivation for these update rules as well. But that's stuff to keep working on. Okay, so I haven't done a toy implementation of the thing I just described, but I have done a toy implementation of basically just this idea that we can implement this kind of matrix vector style composition within the Nengo framework. So how are we going to do this? So first of all, we choose some features to describe animals. So we're going to choose the features. Oh yeah, so sorry, I'm going to talk about the problem first. So I'm using something called the pet fish problem. So what is the pet fish problem? It's basically this idea from it's kind of from the literature on concepts and how to represent concepts. So if we think of a goldfish is not a particularly typical fish. And a goldfish, because most fish are maybe like big and grey and live in the sea and or live in rivers and so on. And a goldfish is perhaps not a particularly typical pet, because a lot of pets are kind of furry and friendly and so on. So it's not a particularly typical fish, it's not a particularly typical pet, but of course a goldfish is an extremely typical pet fish. So if we're representing this within a kind of vector-based framework, we want to say that if we've got a representation for fish, and then we apply we apply this other thing pet to it somehow, we want that resulting the resulting representation of pet fish to be close to the representation goldfish and not so close to the representation of, let's say, shark or even fish. So if we take fish and we apply pet to it, it should move it away from fish and towards goldfish. And it should also move it away from cat and dog and so on, because a fish and a cat are not very similar. So how are we going to think about this? First of all, we're going to choose some features to describe these animals. So we're going to take let's say some features like cared for, vicious, fluffy, scaly, lives in the house is the H here, lives in the sea is an E, and lives in the zoo is a Z. And then and then here I've basically just kind of made up these vectors. So this is why it's completely sort of toy example, more of a sort of proof of concept. So let's say fish are somewhat cared for, fairly vicious. They often live in the they're often scaly, they often live in the sea, they sometimes live in the house, they sometimes live in the zoo. And then we can contrast that with goldfish, which are not vicious, so it's got zeros here, but they often live in the house, and they don't, and they are scaly, but they don't live in the sea. So goldfish don't live in the sea. And then we've got similar features for kind of cat and dog and so on. Okay. And so then, in order to, then what we do is we build this representation of pet. And then we're going to say that we're going to, like, given this representation of pet, we can then compose it with fish. That means unbind fish from it in this case, and then that should give us the representation pet fish. So what is the pet representation? It's, so if you write it out in terms of kind of convolutions of vectors, it will look like this line at the top. If we interpret those convolutions in a sort of matrix format, we get a matrix that looks like this. So again, this is, as I said, it's a completely like toy implementation, and just a proof of concept, but it's something that I'd be interested in kind of digging into further. So what does this matrix say? Well, it basically says, so if we imagine we've got a vector over here, or a semantic pointer for fish over here, when we unbind whatever animal we're representing over on the right here, it's going to say, well, whatever characteristics it has, once it's a pet, it should have a high level on cared for. Okay, it's basically whatever other characteristics it has, we're gonna say now it's a pet, it's definitely cared for. We kind of leave vicious and I've forgotten what F was. Vicious, fluffy, and scaly alone. So if it was vicious, then even if it's a pet, it kind of stays vicious. If it's fluffy, it stays fluffy. If it's scaly, it stays scaly. If it lived in the sea originally, it's now that it's a pet, it's not going to live in the sea anymore. So we've got zeros along here, and then down here we've got wherever it lived. Now it's going to live in the zoo. In the home. Okay, so H was home, so these ones here mean it's going to live in the home, and again, it's not going to live in the zoo. So this is kind of basically just a mapping of how we imagine the adjective pet to transform a given animal vector. And so then we implement this in this software Nengo, and we get quite a nice result. I'm just going to stop sharing that and go to the movie. So here's the movie. This. So I'm going to share. Sorry, I just have to try sharing again. There we go. Cool. Okay, so this, so I wanted to actually give the software, but it's not working, annoyingly. So I just have a movie for you. So in this, what do we have? We have, I've basically built a network in this software Nengo, and spiking neural network software, which implements vector binding using circular convolution and unbinding using circular correlation. And what we do is we give it an input, which is a noun, and the noun has a set of features. And then I've built so what this kind of big block here gives us is a binding with the coefficients that I gave before of certain of these like semantic pointers for the noun features with the other noun features. We have to have this kind of cleanup area here, and then it outputs these adjective noun features, and it'll then give an output. So what we're going to see a noun input over on the left here that goes through this kind of pet network, and it should output whatever the most similar thing to a pet, whatever it is. So I'll play it for you. Okay, so we've got a pet fish, and the thing that is activated is a goldfish. And then when we put in cat into this pet network, the thing that's activated is a cat. When we put in goldfish itself, we get back a goldfish. a pet dog, we get back a pet dog, which is, and so all of these things are kind of, this is what we want to have. A pet shark, what do we get back? A pet shark, we just get a generic fish. So, and then a pet lion is most similar under this representation to a dog. It would have been nice if it had been cat, but dog is okay, I think. So yeah, so this is really, as I say, this is really just a kind of proof of concept that we can do this kind of matrix vector multiplication to represent adjectives and potentially in the future things like transitive verbs and so on, in a way that in this kind of spiking neural network. Okay, I'll go back to the slides. Okay, so yeah, so just in summary, so what have I said here? Basically, I've said this area that I work in, compositional distributional semantics, is nice and flexible, but it's not very cognitively motivated. I've argued that it potentially has advantages over some representations of language that are used in VSAs. And I've kind of shown that there's a mapping from these compositional distributional models into VSAs, and that allows us to then use these compositional models in these spiking neural networks. So yeah, future work is basically completely wide open. I really want to develop the theory and the implementation of this and think about what limitations are and what benefits you might have in practice. So thank you all very much for listening. Please do feel free to contact me on that email address. And yeah, that's it from me. Thank you.
Marta, thank you very much. Thank you very much for this exciting talk, indeed. And now I open the floor for questions. So just before this, I want to point out that we have very representative audience today. So, and I hope for a great discussion on this topic. So please. Who is first? Tony.
Yeah. Hey, Martha. That was really interesting stuff. I really like the examples you had. I think they demonstrate the sort of things that need to be thought about in in terms of how you put these representations together. When you were going through these examples, I was thinking about the embeddings that are already created by large language models, and so it's like you can go to the OpenAI has a service where you can give it text and you get back an embedding. And I was wondering whether you tried anything or thought about trying, like to look at those embeddings and see what their properties are, and try those on your task and see if they fall down, and if they have gaps in their performance, and if they do, whether you can sort of tune them to perform better by using the sort of techniques that you're experimenting with.
Yeah, so not so much exactly with kind of your kinds of approach here. But, well, no, actually we do that a little bit. But yeah, so one thing that we've done is to look at this model. There's a model called CLIP. So I don't know if you know CLIP, but CLIP is like a kind of backbone to some of these image generation models. And what CLIP does is it has a big neural network that processes images and spits out image embeddings, and a big neural network that processes text and spits out text embeddings. And basically what we've done is we've tested it on some of these kind of concept binding tasks. So we've given it things like, pictures of a red cube and a blue sphere, and asked it to distinguish between that and a blue cube and a red sphere, for example. And CLIP on its own is not very good. CLIP fine-tuned is also pretty crappy at doing that as well. And so one of the things we've done is we've actually taken out the text encoder part of CLIP and replaced the text encoder bit with these compositional distributional models, also also a kind of convolutional, red convolved with adjective plus cube convolved with noun kind of representation, and the kind of matrix, the compositional distributional models do a lot better than CLIP itself. Irritatingly, the convolutional models didn't do so well, and I can't quite work out why that is. I think I'd be really interested to kind of think about why they're not so good at that. Or actually, no, they might have been okay at the two. So we also had a relational one where we're kind of saying that there's a cube left of a sphere, and it has to contrast that with like a sphere left of a cube or a cube right of a sphere and so on. So all these kind of difficult things that it has to do. And yeah, the convolutional models were not so good at that, which was frustrating. So the short answer is we have done some work on these big neural models. We find that in training they're really good. A lot of them are really good at training up. But what we also do is we also want them to be able to do compositional generalizations. So like we might show them in the training, they might see blue spheres, but not blue cubes, and they might see red cubes, but not red spheres. And so we train them on one set of label compositions and then test them on another set of label compositions. And yeah, that was difficult. We couldn't really get very good performance on that, which is frustrating, right? Because this is like the whole, kind of the whole point of this sort of approach is that you ought to be able to like take the representations apart and recombine them and get it to work. So that's another area that I definitely want to look into more as well, kind of improving those. But yeah, thank you very much for your question and for your comments. Thanks.
Thank you.
Maybe a small follow-up question, Marta. So yeah, I mean, this work that you mentioned sounds really exciting. Did you publish it anywhere? I mean, on studying the embeddings and the properties of
it is out now. Let me pop the archive link into the
thank you.
yeah. Let me, I'll put, yeah. If there's, while I look up the link, if
absolutely.
there's any other questions, yeah, go ahead.
Ross, you are muted yourself, please.
I did. Thank you very much for that, Martha. I've got a conceptual point, I guess. So this deals with the pet goldfish problem and probably also the fluffy cat and dog. It seems to me that, I mean, because, and you've said quite clearly, this doesn't address the sort of the cognitive aspects. It's sort of purely the formal linguistics aspects of it. And it seems to me that in a way makes the problem harder than it needs to be. So if you've got pet goldfish, you're basically assuming that that's all there is, just the linguistic world, and that applying the adjective to the noun has to create the singular distribution, representation, which encodes all the information which is then relevant to the problem. So you're treating it as a functional application, whereas things like I mean, in psychology, if you're looking at similarity structures between things, it's very sensitive to the environment in which it occurs. So instead, you're starting from a standpoint of saying it's that they're task sensitive representations. So it's not determined by just pet goldfish, but it's pet goldfish plus the context of the task that you're asking, and so that under different circumstances, you'd arrive at a different different representation from exactly the same words. You know, you'd need to have the context. I said it made it easier, but I mean, it's easier in the sense that you're not expecting the adjective to do all the work, but on the other hand, it's a hell of a lot harder because you've got to work out how you get the context to inform the combination. Are you collaborating with Melanie Mitchell at Santa Fe?
Yes, yeah, I am.
Yeah,
So-
because I mean that whole notion of construction of representations driven by the task is it's very much her line of work from decades ago.
Yeah. Yeah.
So I'm just so I'm just wondering what your thoughts would be on that. I mean, because it's essentially it's an issue from treating the problem as linguistic rather than cognitive.
Yeah.
Your musings on that?
Yeah, no, so I agree. So it's basically it's putting a lot of emphasis on what this adjective representation has to do. On the one hand, I think overall I definitely agree with you that you do have to kind of think of that it would be much better to take context into account, and I haven't really thought about that in this context, and I think that it would be nice to do that. On the other hand, basically because you're using these big matrices and larger representations, there's more space. Basically, there's essentially more space for the adjective to do its job. It's not, although actually, having said that, within a convolution with circular convolution, it's going to be, you haven't got as much space to do that. So yeah. Just on an aside from that, I recently read a nice paper in this area of the clip model that I talked about, where basically what they did was they did do this kind of, so we didn't get very good results from clip, but what they did was they actually did apply this kind of context approach by basically calculating a vector that you could add on to or subtract out. I can't remember which one, but anyway, they had a vector that kind of basically meant that you then center your representations in the domain of whatever those representations are. So, if it's all, if it's some colors applied to some, everyday objects, then basically they take the vector embeddings that they get for all of those, center it on wherever those are, and then do they're doing some additive decomposition, and they find that it works a lot better. So potentially that sort of thing, by using that kind of translation mechanism in the space, given some context. So if we say we're given context, because you have to be given context in order to be able to use it, maybe there's something that we could do there to sort of add that in, basically. Yeah.
Okay, thank you very much.
Marta, we have a question. We have a question in the chat from Howard. Can you please read it, and also that I have time.
Yeah. It says, so the question in the chat is, are you using the same tensor operations on VSA as in compositional distributional semantics? So yeah, the idea here is basically that if you take a kind of Smolensky style architecture where you have a binding operation being tensor product, and an unbinding operation being inner product or dot product, then you can basically do a really direct mapping between the compositional distributional semantics that Cook, Sadrazadeh, and Clark developed. There's a very direct mapping between that sort of representation and a Smolensky style role filler binding representation. But then from there, the idea is that we're going to say, okay, well, we don't want to use this Smolensky style representation. What we actually want to use is the convolution and correlation operators for the binding and the unbinding. So there should be a pretty direct mapping between them. But I don't know. I would like to formalize that more. I think there's some formalization to be done there. And you've also said what type of VSA are you using? It's not binary. It's just kind of any kind of value on the vectors. Real value vectors. Yeah.
Thank you.
Cool.
So let's see. Do we have any more questions? So let's give it a chance. Ross?
If no one else is putting up their hand, I think I'd like to actually put Penty on the spot. Is Penty still on the chat, on the call?
Well, at least his name is.
Yeah, I just wonder. I mean,
okay, so what's
yeah.
the spot? What's the spot?
Sorry, with Martha's hand wavy learning mechanism that she presented, that looked to me reminiscent. Thank you, Martha. That's very helpful. Reminiscent of random indexing. I was just wondering if you thought it was had some relationship across to random indexing.
Well, I can't just say offhand. I would have to sort of look at it first. But random indexing, basically, random indexing is the same as random projection. And so if you project something into a high-dimensional space randomly, you get random indexing. And so I guess that's all I can say at this point.
Was it the work you did with Magnus Sahlgren, or is it on? Well, maybe I've got the name wrong.
Yeah. Okay. Well, there's one
on learning iteratively representations of words.
Yeah. Well, there's one thing that we use is we used, in addition to addition and multiplication, we used permutations. And permutations, we introduced order, and certainly in the English language, order matters. And so sometimes I wonder whether when you feel that you should use a matrix multiplication, like an adjective is a matrix multiplication, that maybe that would be done with just permutations. Permutation is a matrix multiplication, but of course then you'd have more noise. So you'd have to, so you'd stay in the same mathematical space. You wouldn't have to introduce any, like in tensors, you know, the representation keeps growing. If you can accomplish the same thing with permutations, you know, it sort of fits better into this model that we work on. So, but just comments.
Thank you. Sorry to pull you sideways like that. Cheers.
Ambushed.
Okay. Any more comments, questions? Then looking at the clock, so the time is late here, anyways, in Sweden. So I would like to thank you, Marta, once again for being with us and giving this wonderful talk. So, so the recording will be available very soon on the website. So I thank you all for attending this webinar, and see you in 2 weeks from now. Thank you.
Great, thank you, and thanks again for the invitation to give the webinar. Thank you very much.